Then we wanted to apply the p-type aluminum nitride to devices, but at that time we did not have a source of n-type aluminum nitride inside our MBE chamber. So uh, the breakdown field of semiconductors is scales with the band gap of semiconductors, and we know that the critical electric field of aluminum nitride is approximately 3 times that of gallium nitride, resulting in a theoretical improvement in terms of Baliga's figure of merit for aluminum nitride over gallium nitride of approximately 17.5 times. Some exciting applications of aluminum nitride-based devices are operation in extreme environments, high-temperature electronics and sensors, power distribution, and high-power radio frequency electronics. Some other amazing applications of aluminum nitride include deep UV LEDs and lasers, solar blind detection, and acoustic devices. My major motivation for this study is that aluminum nitride ranks in the top 2 materials in terms of ultra-wide bandgap semiconductor performance parameter. For example, the critical electric field of aluminum nitride is 1.5 times that of gallium oxide, 3 times that of gallium nitride, and approximately 5 times as compared to that of silicon carbide. But up to now, the major limitation was p-type doping, the lack of doping in aluminum nitride. And we first proposed the rhythm-doped aluminum nitride p-type films grown via metal modulated epitaxy. The solubility limit of a dopant is determined by the formation energy of the dopant. Formation energy further depends on the atomic radii matching and the bond strength of the host versus dopant atoms. We know that in case of gallium nitride, magnesium closely matches in terms of atomic radius with the radius of gallium in gallium nitride, so it is found to be the best p-type dopant in gallium nitride. By similar hypothesis, beryllium closely matches with the atomic radius of aluminum in aluminum nitride and is potentially the best candidate as a p-type dopant in aluminum nitride. Generally, the theory agrees that the activation energy of beryllium is lower as compared to the activation energy of magnesium in aluminum nitride. The activation energy of beryllium in aluminum nitride is found to be approximately 300 milli-electron volts. In traditionally grown magnesium-doped gallium nitride, we find isolated impurity levels, which is also depicted by its 2 peaks in photoluminescence measurements. Now, on the contrary, in metal modulated epitaxy, we can achieve high solubility, and also we achieve impurity band formation overlapping the valence band of the semiconductor, which is also depicted by a single photoluminescence peak where the band overlaps that of the gallium nitride 3.4 electron volts band gap. So we have achieved an improvement in terms of activation energy for magnesium doped gallium nitride, reducing it from 200 to 50 milli-electron volts as compared to literature. So now we wanted to see if we can improve the activation energy of beryllium in aluminum nitride as well. This led to my study of growing beryllium doped aluminum nitride on top of HEPE aluminum nitride templates with buffer layers. We achieved streaky reflection high energy electron diffraction patterns indicating smooth surface morphology. From AFM comparison of a beryllium doped aluminum nitride versus undoped control sample, we see that beryllium doping improves the surface morphology. Later, I deposited platinum, palladium, gold contacts on these films for Hall measurements. And from extensive optimization of the contacts, here I've shown a comparison of the post-annealed beryllium doped aluminum nitride versus pre-annealed contacts. And the annealing improves contacts conductivity by approximately 6 orders of magnitude. Furthermore, from comparison of a beryllium-doped aluminum nitride versus annealed undoped aluminum nitride film, we see an improvement in approximately 4 orders of magnitude. So it's actually the beryllium doping which improves the conductivity of these samples. Later, I wanted to validate the conductivity type of these samples with both Hall measurements and also hot probe measurements. But first, I calibrated Hall and hot probe measurements for our standard p-type, UID, and n-type gallium nitride samples. Later, I grew beryllium-doped aluminum nitride samples at a substrate temperature of 600 degrees C at different beryllium doping levels. Beryllium doping levels where the Hall results were questionable, beryllium doping levels where we see massive compensation, and beryllium doping levels where we achieve reliable results in the range of 10 to the power of 15 to mid 10 to the power of 17 per centimeter cube, resulting in activation efficiency of approximately 5%. I also grew beryllium-doped aluminum nitride at 700 degrees C growth temperature and achieved even higher hole concentration of 3 into 10 to the power of 18 per centimeter cube. And the conductivity type was also validated from hard probe measurements. Later, we sent these samples to Lakeshore for conductivity confirmation and also for temperature-dependent Hall measurements to extract the activation energy of these samples. And we found a very low activation energy of 37 milli-electron volts. We performed a study on p-type aluminum nitride-based heterojunction diodes with Schottky, pin, and junction barrier Schottky character, achieving significant breakdown performance. Schottky diodes have the advantage of low turn-on voltage, but they also have low breakdown performance. Pin diodes have higher breakdown performance, but also higher turn-on voltage. Junction barrier Schottky, or JBS, is a new kind of diode which has advantages of both Schottky and pin. It has low turn-on voltage and also high breakdown performance. Currently, there are two approaches for conventional JBS diodes. One involves ion implanted p-type regions, but it requires activation of the dopants. Another approach requires etched and patterned p-type regions, and it suffers from high etching damage. So we introduced a novel approach to grow MME Schottky, pin, and junction barrier Schottky diodes. We know that the lattice mismatch between aluminum nitride and gallium nitride is approximately 2.4%, and above a certain critical thickness, the growth of aluminum nitride and gallium nitride is going to result in high crack density. So we utilize the intentional crack density of aluminum nitride and gallium nitride to grow novel Schottky, JBS, and pin diodes. And this figure shows the layer structure diagram of my growth structure. We have an N-type gallium nitride film, then an I-type gallium nitride film, and then beryllium-doped P-type aluminum nitride film. And the crack density of the top film is controlled via beryllium doping and growth conditions. The density of the deep and wide cracks determines the behavior of the diode. High density of deep and wide cracks resulted in Schottky behavior. Films with no open cracks resulted in pin diode behavior, and films with medium density of deep and wide cracks resulted in junction barrier Schottky behavior. Here I am showing the JV characteristics both forward and reverse of these diodes. These are representative figures. We see that for the Schottky diodes we observe low turn-on voltage but also low breakdown performance. For the pin diodes we see high turn-on voltage and high breakdown performance. And for the junction barrier Schottky diodes, we achieve a low turn-on voltage of 1.5 volts and a high breakdown voltage of approximately 20 volts. And from early quasi-vertical electric fields demonstrated in these devices, we achieved a field of approximately 1.25 megavolts per centimeter, which is at the high end of MBE achievable breakdown critical electric field performance, both in case of quasi-vertical and also in case of fully vertical devices. In the previous slide, I have shown representative results. However, we have shown results for multiple samples and multiple devices, which are summarized in this slide.